This lecture deals with finite automata. So we have to discuss the basic concept behind finite automata. Finite automata is also termed as finite state machine. So before going into detail, let us discuss the schematic diagram of a finite automata. So one important component of finite automata is one-way infinite tape that is divided into unit cells. So these are actually unit cells, and each cell can hold a single alphabet. So this is one important component. Then next component is a finite control. A finite control that translates within a finite set of states. So let the states be Q0, Q1, Q2, Q3. So this is the heart of this machine, which will be in a state within a finite set of states. Now the third component is a read-only head. A read-only head which is capable to read one symbol from the tape at a time. And here we proceed based on the assumption that initially this read-only head will refer to the leftmost cell of one-way infinite tape. Now this machine actually translates within it. These three components together form finite automata, and let the input be. This tape is actually used to store the input string. So as you all know, string is actually sequence of alphabets. So if you talk about finite string, you can define finite string as finite sequence of alphabets. And if you talk about infinite length string, that is actually infinite sequence of alphabets. So let us consider finite length string. So here it is pretty clear that length of string is 4. So length of string is based on number of alphabets in that string, number of symbols, input symbols in that string. So input string will be loaded starting from the leftmost cell of this tape. That is another assumption. So it will be loaded like this. So again we assume that there will be a starting state. So let the starting state be Q0. Assume that Q0 is the starting state always. And depending upon the state, current state, so this is the current state. Depending upon the state and the input symbol, transition takes place. So depending upon the state and input symbol, transition takes place. Transition in the sense, assume that from Q0 for input A, it goes to Q1. Now at the end of or during that transition, after the state change, this read-only head will advances one unit to the right. Now it is clear that machine is in state Q1. From state Q1, assume that input is B. If input is B, let Q1 or the state of this machine changes from Q1 to Q3. So after or during this transition, the read-only head will advance one unit to the right. Now current state is Q3. From Q3, let the input encountered is B. So assume that it goes to Q2. And at the end of the transition, this read-only head will advance 1 unit to the right, and current state is Q2. And from Q2, let the input encountered is A. So from Q2, for input A, assume that the state of finite control changes to Q3. And after a sequence of transitions, whenever the string expires or whenever this model completes reading the entire string, if state turns to one among the final states. So if Q3 is a final state, then the string is said to be accepted. By completing read operation of the entire string, if the machine or the finite control ends up in a non-final state, then the string is said to be rejected. So that is the working of this particular model. So basically, finite automata acts as string acceptor. String acceptor. So this model actually accepts set of strings that are valid and rejects set of strings that are invalid. Once more, I will repeat the string acceptance condition for this model. This model will start reading the input string from the leftmost cell, starting from the first symbol, and it will scan or read the symbols one by one in the input string from left to right and takes transition. After completing reading operation of the entire string, if state of machine reaches one among the final states, then the string is said to be accepted. Otherwise, if model ends up in a non-final state, then the string is said to be rejected. So from this itself, it is clear that you can categorize states into final state and non-final state. So as I said, there will be set of states and finite set of states, and this finite set of states can be partitioned into non-final states and final states. And again, as I said, there exists one unique state that acts as starting state. So always machine will, before reading operation before consuming the input string, machine will remain in the starting state, or will be in the starting state. So this is the schematic diagram of finite automata, and this finite automata get classified into deterministic finite automata and non-deterministic finite automata. So in this lecture, we are focusing on deterministic finite automata, and based on this schematic diagram, let us formally represent this finite automata. So we are dealing with deterministic finite automata. So deterministic finite automata, abbreviated as DFA, is formally defined as M is equal to Q sigma delta Q0 F. So these are the different components of a deterministic finite automata, where Q is the non-empty finite set of states, sigma is the non-empty finite set of alphabets or input symbols, delta is the transition function that maps from Q cross sigma to Q. So delta is the transition function that maps from Q cross sigma to Q. Then, as I said, Q0 is the start state or initial state. Again, F is the non-empty finite set of final states. So from this it is clear that for a deterministic finite or DFA to exist, there should be at least one final state. So Q, at least one state. So Q is the non-empty finite set of states. So that set of states must be non-empty, and that set must be finite. So that is the reason for calling this model as finite state automata or a finite state machine or finite automata. Then sigma is a non-empty finite set of alphabets. In the sense, the set of input symbols must be again non-empty, and again that must be finite. So that is another reason for calling this as a finite model. So input alphabet set is finite and the set of states is also finite. Then delta is a transition function. So as we have discussed earlier, depending upon the input, depending upon the current state and the input transition takes place. So we have to define the transition function, and that function maps from Q cross sigma to Q. So we can discuss this function mapping later. Then Q0, as I have mentioned, it is the starting state or initial state. That state is actually unique, and in our case we will always fix Q0 as the start state. Then F is the non-empty finite set of final states. In the sense, there must be at least one final state. Okay. And from this it is clear that F will be a subset of Q. You will be having set of states in the DFA, and from the set of states there exists a subset which will be the set of final states, and that subset must be non-empty. So let us discuss an example. So when we talk about DFA, we can have different representations. So first representation is transition diagram. Transition diagram. So let us consider this example Q0. This is the start state. Start state is always designated with an incoming edge or arrow without any other state in the other end. So this is the incoming edge. Let the second state be Q1. Let that state be final state. So we always designate or represent final state using double circle. All remaining states will be designated using or represented using a single circle, and transitions will be represented using edges with label representing the input symbol. So from Q0, assume that for input A, it goes to state Q1, and from Q0 for input B, assume that it remains in the same state. Now from Q1 for input A, let the machine goes to state Q0, and from Q1 for input B, let the machine remains in the same state. So this is what I meant by transition diagram. This transition diagram actually represents a particular DFA. So here you are having two states, Q0 and Q1. From this it is clear that Q1 is the final state because it is represented using double circle, and you know that Q0 is a non-final state, and again Q0 is a starting state because it is having an incoming arrow or edge from outside. And these are the transitions. That is, from state Q0, if the machine reads input A, it will go to state Q1. From Q1, if machine reads input A, it will go to state Q0. From Q0, if machine reads B, it will remain in the same state. From Q1, if machine reads B, it will remain in the same state. This is transition diagram. That is the diagrammatic representation of a finite automata or deterministic finite automata is called as transition diagram. And this transition diagram is actually represented using directed graph. You can call it as a diagraph or a directed graph because edges or transitions are represented using directed edges. So this is a directed edge, this is a directed edge. So edge actually connects these states, and since there exists direction, you can call this as a directed graph. Now, what happens if I supply feed input A, B, B, A to this machine? So, if we trace the transition path from Q0, it will read A. From Q0, if it reads A, what about the target state? From Q0 for A, it will go to state Q1. Now, the read-only head points to the next symbol. So, from Q1, it will read B. From Q1 for B, it will remain in the same state. It will remain in the same state. And the read-only head advance one unit to the right. Now from Q1 it will again read B, so it will remain in the same state. For B it will remain in the same state. Now the read-only head will advance one unit to the right, and from Q1 the input encountered is A. So from Q1 input encountered is A, it will go to state Q0. So from at this point it is clear that this machine has completed reading the entire string. So after completing read operation of the entire string, check whether machine reaches final state or not. So here machine is in state Q0, which is a non-final state. So this string is rejected by this machine. This string is said to be an invalid string. Now let the input string be A, B. So let us see what happens for this input string. So initially machine is in state Q0. We can trace the transition path. From Q0 it will read A. From Q0 by reading A it will go to state Q1. So it will go to state Q1. Now from Q1 it will read A. From Q1 for input A, it will go to state Q0, and the read-only head will advance one unit to the right. Now from Q0 input encountered is A, so it will go to state Q1. Now from Q1 next input encountered is B, so it will remain in the same state. So for input B, the machine takes the transition path A, B and end up in a final state, and this string is said to be accepted or accepted string, or you can call it as a valid string. This string is said to be rejected, or this string is said to be an invalid string. So after a sequence of transitions, by completing read operation of the entire string, machine ends up in a final state, then the string is said to be accepted. Let us move on to another representation, that is tabular representation. Tabular representation, that is transition table. Transition table. So you are having machine name. You are having only two alphabets, A and B. So in this way you are representing alphabets. So as I said, set of alphabets is represented using sigma. So set of alphabets is set AB. Now here you have to write set of states. You are having state Q0 and Q1. So you can write set of states in this column, and you have to differentiate start state and final states. So here this is the start state, so you can represent using an arrow. You can designate using an arrow, and final states must be designated using asterisk symbol, attaching asterisk symbol. So if you are having, you can have multiple final states in the finite automata, and you have to designate all those final states using asterisk symbol. Now from Q0 for input A, it goes to state Q1. Now from Q0 for input B, it will remain in the same state. Now from Q1 for input A, it goes to state Q0. Now from Q1 for input B, it will remain in the same state. So this is transition table, that is tabular representation of finite automata or DFA. Next one is mathematical or formal representation. So this is diagrammatic representation, this is tabular representation. Now we are going to discuss formal representation or mathematical representation. So I can represent this model as M equal to Q sigma. You have to use the formal definition, Q sigma delta Q0 F. You have to define each components. So what about Q? Where Q equal to, you are having two states, Q0 and Q1. Set Q0, Q1. So here you are having finite set of states. Now second component is sigma. What is sigma? Sigma is set of alphabets. So what are the alphabets that you are using in this automata, or the input symbols read by this model? A and B. Again this set is finite. That is why we define sigma as non-empty finite set of alphabets. So finite set of alphabets. Now you can define delta. Delta Q0A. What is delta Q0A? What is delta Q0B? Now what is delta Q1A? What is delta Q1B? This function takes two parameters. First component is state and second component is age. So from Q0 for input A, it goes to state Q1. Now from Q0 for input B, it will remain in the same state Q0. Now from Q1 for input A, it goes to state Q0. Q1 for input A, it goes to state Q0. From Q1 for input B, it will remain in the same state. Now the last component is F. Q0, you know that it is the start state. And what about F? F is the non-empty finite set of final states. You are having only one final state in this model, that is Q1. So all these representations actually represent the same mathematical model. Okay. Now in the formal definition I have mentioned that delta is the transition function that maps from Q cross sigma to Q. What is the reason? If I take these transition functions, the left hand side is actually an element that belongs to Q cross sigma. So Q cross sigma in the sense Q0A, Q0B, Q1A, Q1B. And the right hand side is an element that belongs to set of states. And if we look into this transition function, for each state there exists unique transition for the input symbols. I will make it clear. If I take Q0, it is having exactly one A transition and exactly one B transition. If I take Q1, there exists exactly one A transition and exactly one B transition. So since there exists unique transition for each and every state for all the input symbols, the machine or this model is termed as a deterministic model. So if you are asked to design a deterministic finite automata for some particular language, you have to ensure that you have to make sure that each and every state are having unique transition for all the input symbols. Now let us define language accepted by this model. So what do you mean by language? Language accepted by DFA. Let us consider this example. So let this model be M, DFA be M. Then language accepted by DFA M is defined as L of M. So L of M is equal to set of strings accepted by M. So what about the set of strings accepted by this machine? So if we look into this machine, it accepts A. It accepts A, B. It accepts B, A. It accepts A, A, A. It accepts A, A, B, A. And so on. Again, if I consider another string A, B, A, B, A, B, A, B, etc. So this machine actually accepts infinite number of strings. Now, actually, if you analyze each and every string accepted by this machine, there exists a common property, a common feature for all the strings. So each and every string recognized this machine contains odd number of A's. Odd number of A's. So this machine accepts strings generated using A's and B's containing odd number of A's. Now let me formally define language recognized by this model, L of M. L of M is equal to set W belonging to sigma clean closure. So sigma clean closure in the sense set of all possible strings that can be generated using alphabets that belong to sigma. So in this case, you know that sigma is equal to set AB. So sigma clean closure means all strings that can be generated using A's and B's including null string. So W belonging to sigma clean closure such that delta cap Q0W is equal to QF, where QF belongs to F. So here delta cap actually represents extended transition function. So L of M contains set of strings that belongs to sigma clean closure. So if I take sigma clean closure in this context, it contains epsilon, it contains A, it contains B, it contains AB, BA, BBA, AAB, and so on. All strings generated using A's and B's including null string. So from this set, there will be a subset of strings that contain odd number of A's. So all such strings will belong to L of M. So W belonging to sigma clean closure such that this is the condition. Starting from start state, by consuming the entire string W, if it reaches final state, then that W will be a member that belongs to L of M. So all such W's together form L of M. So in this way you can formally define language recognized or accepted by DFA M. So language recognized by DFA M is defined as L of M equal to W belonging to sigma clean closure such that delta cap Q0W equal to QF, where QF belongs to F. So let us take an example. Consider the string ABB. So how will you formally show that ABB is accepted by this machine? It is simple. You can use extended transition function delta cap. Machine always starts from starting state Q0. So Q0 input string is ABB. So this is equal to delta cap delta Q0A BB. So it will from state Q0 it will read input A. So that is this transition function. So what is delta Q0A? Delta Q0A is Q1. So this will be equal to delta cap delta Q0A results in Q1. So Q1 BB. Now you can rewrite this as this is equal to delta cap delta Q1B B. So what is delta Q1B? Delta Q1B is Q1 itself. So this will turn to delta cap delta Q1B results in Q1 itself. So Q1, the remaining string to be consumed is B. So this is equal to, what about Q1B? That is delta Q1B, which is equal to Q1. And check whether it ends up in a final state. Since Q1 is a final state, this string is said to be accepted. So if I take input string AA, so this string is said to be accepted because by applying extended transition function, it will end up in a final state. Let us consider string A. How will you show that this string is an invalid string? Let us apply extended transition function delta cap Q0A. So if we expand this extended transition function to this state, apply input A. For that you have to use transition function delta Q0A. What about the remaining string? Remaining string is A, comma remaining string A. Now apply this transition delta Q0A. Delta Q0A is Q1. So this will turn to Q1 remaining string A. What is delta cap Q1A? This is equal to delta Q1A. What is delta Q1A? Delta Q1A is Q0. Check whether Q0 is final state. Q0 is not a final state. So this string is said to be rejected. So in this way you can use extended transition function to formally show that show the acceptance of valid string and the rejection of invalid string. So this is all about deterministic finite automata.